In this video, we will introduce the convolutional neural network. And for a typical feature extraction network, we will using all the input features to calculate the output features. For example, here, if the X is a two-dimensional image, and in order to calculate the one output pixels, which is in the I and J position, we will use in the AB pixel in the X to try to using all those value to decide the value of this one. And actually, we will using a weighted sum W here. So mathematically, we can write this equation in this way. The XKL is the AB pixel. So the K and the L will be a dimensional index for the whole image here. So basically, the XKL it will be every pixel in the image. And then we will using the weight W here, which is indexed by IJKL. So for every pixels, we will has a weight WIJKL for to calculate the weighted sum over all the positions and using that to produce the H here. And we can see that the W here has the index IJ. It means that for each position here, we will using a different weight to calculate the output from the input. And but it's obvious that we can see that the complexity will be, since we know for each of the Hij here, we need to do the n square multiplication, and but we have n square pixels, so the total complexity will be n power of 4. So and it's obvious that the computation cost is very high. And so sometimes we will try to rewrite the above the equation to the other one. Actually, we just using the I plus A to replace the K and the J plus B to replace the L. And then the IJK will become the IJAB here. Okay, these two are actually the same. But if we limit the range of the AB, for example, the KL is from 1 to n, but for the AB, we might constrain it in a very small range. So in this way, the computation will be reduced a lot, because for each of the Hij, we only need A multiply B operation instead of n squared. So if A and B is just, for example, a number of 3, so this would be just a line operation instead of n squared operation. So this will become a constant. So the complexity will be reduced from n power 4 to the n power 2, since we have n power 2, the n power 2 the pixel here. Okay, but for computer vision task, the translation invariance is an obvious truth, because a dog will be a dog no matter where the pixels of the dog are located inside the pictures. So if a group of pixels represent a dog, which is located in the top of the image, you will be still a dog if those pixels are in the bottom of the image. So no matter the dogs is in the image is still a dog. You will not become a cat just because it's in the bottom half of the image. So we believe that the translation invariance is very important for the computer vision task. So how can we represent the translation invariance? No. So maybe we can look at the formula here. So we know that when we from the previous page, we know that when we want to calculate the output, we can use in this formula here. But if we get rid of the ij here, so it means that the vijab become the vab. In this case, if we have a same group of xi x here, so no matter it is located in the locations, since the vij is not related to the ij anymore, so the result will be the same. So this means that if the x is the same, the h will be the same. So that if we're using the formula like this, we will have a translation invariance, in the mathematical expressions. And actually, the other thing which is very important for computer vision task is the locality. So a lot of when we try to calculate the feature map for image, and in a lot of cases, we only need to care about the pixel around it. So the pixel, one pixel in the left top corner has very low probability to be related to the pixel in the right bottom corner. So we only need to care about the pixel around it, because those pixels will be used to define a feature. For example, a line or a circle or a dot or something. Of course, there is some feature which will need the information from different part of the image, but there's a lot of other features we don't really need that. So how could we have a balance between the locality and the capability of the network? So the convolution, the layers structure of a convolutional network will provide the capability for this, and we will discuss this later. But for now, we only need to know that in order to have the locality here, the only difference between these two is that we try to limit the value of the delta here. So if the delta is n divided by 2, so this 2 will be the same. But if the delta is a very low single digit number, such as the 1 or the 2, this is actually what the convolutional network is. So let's look at the convolution operation mathematically. So the most generic formula for the convolution is look like this. So we have two functions, and their convolution is exactly this function, the integral between the function of z and the g of x minus z. So the second x minus z is where the convolution comes from, because you can see that every point in the f will be act at the x minus z here. So it will be a close. So this is write it in a discrete form. So if we have a lot of different just try to discretize the integral here, you will become this formula. So you will become fa and g of I minus a, and do the summation to get the convolution. And if it's two-dimensional, you will become this one. Actually, this is same just we do the two-dimensional integration here. And actually, this function, if f is v, g is x, so it will become this one. Okay, but in here, you can see that the a is a, b is b. There is no a minus I minus a here, or j minus b here. So there is no minus here. This is just the same as this one. We can ignore the ij here. Just look at the a and the b. Okay. So it seems that this is not a convolution. Actually, mathematically, this operation is called cross correlation. So we will try to look at the correlation of those two functions, v and x here. But so actually the convolution network is actually a cross correlation neural network. But since the convolution is more well known in computer vision, and the neural network is studied from the computer vision task, so they still call it a convolution network. And why we can do that? Well, we can just mix the cross correlation and the convolution. We can using this as an example to extend why we can mix up the cross correlation and the convolution. For example, here we have this is a input image, and this is a filter. So when we execute the convolution operations, actually we just using those four numbers and then multiply by those four numbers. So for example, the first one, the 19, is equal to 0 multiply 0. So this is the first term. And the 1 multiply 1. So this is the second term. And the 3 multiplied by 2. So this is the third term. And the 4 multiplied by 3. So it's the fourth term here. So when we do the calculation, we can get the 1, 6, and the 12, which is 19. So we get the first number as the 19. And we can repeat the whole procedure to get all the four numbers. But you can see that this is a correlation because we multiply it in the same position. So in order to make it the convolution, actually it will become the 0 and the 0, first one, and the 1 to 3 here, and the 1 to 2 here, and the 4 by 3 here. So this is actually the convolution. So the value should be 18 instead of 19 here if we do the convolution. But actually, if you think that we just flip the filter from 0, 1, 2, 3 become the 0, 2, 1, 3. Oh, okay, we just swap the position in advance. And then we can apply this to this convolution. It is actually the correlation between those two, it will be the same. Okay, so we know, so from this example, we know that we can just change to swap the element in the filter to convert between the convolution and the correlation. But actually, we have not decided how to train the model yet. But those filters are decided by the backpropagation algorithm. So that actually, from the point of view of a neural network, we don't really care about how we can write this two, because no, they just swap the position of a number, and those numbers are decided by a backpropagation algorithm. So it doesn't matter we using the close relation or the convolution, because they are actually, for us they are the same, because there's no meaning for the precision here. So if we want, you say that we want to do the convolution between those two, we can just using this one to do the close relation, and it will become the convolution. Okay, so this is why people still call the convolution network, the correlation network, as the convolution network, because convolution, in the computer vision, is the term convolution has been used for a long time to define some kind of filter to detect the edge or detect some other features in an image. So since it has been used in traditional computer graphics for a long time, so when we switch to the neural network, we're still using the same term, and so the people will understand what it is. Okay, so to now we have understand what is the convolutional operations. So we will start to introduce some more idea about how to implement a convolution network. The first feature we need to discuss is the padding. So, for example, here we have a filter, and we have a input feature made like this. Okay, and so initially, actually, all the yellow block here does not exist. We only have a 3x3 the network here. So for the first output, we're using this block to multiply this block. So it will produce the 19 here. And then we move it to the right, so that we're using this block to multiply this block and produce the 25 here. Then we move it to the right again, you become this one here. Since we only have one column instead of two, so it's impossible to multiply this two. So there's two choices here. The first is that we just drop this one. So we just produce the 2x2 feature map here, which is smaller than the original 3x3 feature map. If we want to keep the size unchanged, we need to define how we can multiply those two blocks together. And the obvious way is that we can pad some value after here. So for example, here we pad the zeros here, and so that we just multiply these two blocks to produce the 10 here. And then we can move it down to do this and this, and we can get a 27 and the 14 and the 43 here. but after this line we can move it down again, so we see the similar situation to the right of the matrix. We have the 1 by 2 vector here, but this is 2 by 2 filter. So how could we do the convolution between them? So we just extend it to add some padding below the 6 and the 7, so that we can modify them together to get the value here. And actually those two multiplied together will be actually the 7 here, because this is 0 and these two are 0, so only non-zero term is 1 multiplied 7, so it will be 7. Okay, so this is called padding. So the yellow block is called padding. But in this case, there's one strange thing here, because we only pad in the right and the bottom side. There's no padding in the top and in the left side. So it means that you will break the symmetry, because we just pad in one side, doesn't pad in the other side. So typically, we want to keep the symmetry here. So typically we will not using the 2 by 2 CNN. So for most cases, we are using the 3 by 3 or 5 by 5 or 7 by 7. We are using those odd number of the kernel with the odd number of the size. Okay, so the next thing we need to discuss is the stride. In the previous example, for example, if we multiply these two matrices, so the first one is here, okay, and then the second one, if we move it by 1, so it will be this one. Let me use in the other color. So it will be this one. And then the next one will be this one. Okay, so for every time we move the to 1 pixel to the right, and when we reach the right of the input, we just move it 1 pixel down. Okay, but instead of moving for the 1 pixel, we can actually move more than 1 pixel. For example, the first one is here, and we were using the second one here. So actually we will move 2 pixels. So this is called stride. By using a stride, we will reduce the resolutions, since we move 2 pixels for each time, so that the output will be the 1/2 of the resolution in both the width and the height. So the future map will be reduced by 1/4. Okay, so since the convolution only using nearby pixels only, so for an output map which produced by 2 by 2 filter, every pixel in the output map depends on only 4 pixels in the input map only. For example, for this pixel, he only related to those 4 pixels only. He doesn't relate it to those 2 and those 3 pixels. He only related to those 4 pixels with green. mark there. Okay, but if we were using this one and we apply the other 2x2 filter here, okay, so we know that this related to those 4 pixels. Let me try to start it. This will be related to those 4 pixels. But this one will be related to those 4 pixels. And the 2 here will be related to those 4, and the 43 will be related to those 4. So it means that if we apply this to this and produce the output map here, this pixel will relate to all 9 pixels in the input image. So it means that if we stack, although the 2x2 filters will relate to the 4 pixels for each output map, but if we stack 2x2, it will become a 3x3. So this 2x2 and 3x3 will be called the reception field. It means that in the reception field for each input will be decided by the CNN operation between it and the input, so that it will decide when we try to decide the number here, if we change the number in the image, if it will affect the value of the output or not. So this will call the reception field. So it will be obvious that if we stack the network together, so when the network is deeper, so the output here will relate to a large area in the input image. Since when we stack every CNN operator, it will actually increase the reception field. Okay, so now we will try to understand how to calculate the CNN network. And I believe there are some people here have some misunderstanding about how to apply the CNN operations. And I am one of a couple of years ago when we start to learn the CNN convolutional neural network. Okay, so let's try to understand it in more details here. So if we have typically we will have multiple channels in each layer of the network. And for example, for the color image, we will have 3 channels, and each of them one of them are red channel, the other are green channel, and the other are blue channel. And when we try to and in the middle of the neural network, we may have hundreds of channels in each layer. But typically, the filter does not share between the channels for the convolution layer. Therefore, if we have 2 channels, we will have 2 sets of filters. In this example here, when we try to apply the kernel to the input, actually, since we have 2 input channels here, we will have 2x2 filter, and each of them, the filter will apply to 1 input channel. So it means that when we do the convolutional operation, we will have a different filter for the different input channel. And then this input and this will produce 1 output. And And then this one and this filter will produce this output. Okay, so it means that we will have a two set of CNN operation here, and then actually we will add them together to produce a single output channel. Okay, so this is the first misunderstanding some people might have. So some people might assume that we will produce the two output channels since we have a two set of filter here. But actually, we will add them together to produce a single output. And the output will be the sum of the result of all convolutional result. Just these two, we will add them together to produce the output. So it means that no matter how many input channel we have, we will produce a single output channel. But what happens if we want to have a multiple output channel? In this case, we need to have multiple set of filter here. So for each set of filter, we will apply this set of filter to each input output and to produce the two set of the output and add them together to produce one output. And then if we need to have a second output, we need to provide another set of the filter here so that we can produce the other output. So it means that the number of the parameter will be decided by the KH and the KW here. In this example, this will be 2 by 2. And we must multiply it by the input channel because in here the input channel is 2. So for each set of filter we have 2 filters. And then we multiply it by the number of output channel we need. So in here is 2 as well. So for this example, we will have a 16 parameters. So we can just count here. We have a 4 and 8 here, and 2 8 is 16. We have totally 16 parameters for those for the neural network layer with 2 input layer and 2 output layer. Okay. Till now, we have understand the basic CNN operation, and we will learn some more advanced operation which make the convolutional network more powerful in the next video.